So, okay, it is 2 o'clock my time, which is Mountain Time, 4 o'clock Eastern, and we are very pleased to have another in the Next Generation Science Standards Earth and Space Science webinar series that has been supported by National Association of Geoscience Teachers and by AGI. So today, I want to point your attention to the chat window. If you have questions or comments that you want to make on the presentation, you're welcome to use the chat window just to let us know what you're thinking. And this will be archived for later viewing. If you're on the NAGT discussion list for NGSS, then you'll get a notice of that, and I will put that link into the chat window directly. I wanted to make you aware. I'll show a future event in a moment, but we have a couple of presenters today who are going to be sharing their experiences in supporting elementary teachers with implementing next generation science standards. And we know that the whole beautiful vision of NGSS depends on a lot of things, and one of the things it depends on is being able to help elementary teachers do instruction about NGSS science and in the NGSS instructional vision, pedagogical vision. So we have presenters Kim Cheek, and Kim is with the University of North Florida, and Heather Petkovich, who is with Western Michigan University. And they will introduce themselves further as part of their presentation. After Kim and Heather have finished their presentation, we'll have time for some Q&A. Questions will go into the chat, and presenters will be able to address those questions that way. We do have another in this series that's coming up next month. That's May 12th, and that will be Ed Geary talking about how to build a state coalition for implementing next generation science standards in the earth and space sciences. Ed has been working in Washington State along with a number of other people at other organizations, and so I'm looking forward to hearing more about those kinds of best practices and strategies that have led to success. Also, I want to remind you that the Earth Educators Rendezvous will happen in July in Madison, Wisconsin. That's happening from July 18th through 22nd, and there will be NGSS programming as part of the Earth Educators Rendezvous, both in the presentations and in the workshops. And then this is the link I was referring to, and I'll just dump that into the chat. But if you are signed up at this link, you can find a list of all the archived webinars and links to those, and you can also get on the list so that you're aware of upcoming webinars and you know when these archived webinars are available for you to send to your colleagues or look at again. So with that, I'd like to turn it over to Kim and Heather, and thank both of you very much for discussing this very important topic.
All right. Thank you, Susan. Kim here, and we'll go ahead and get started. So obviously, our goal today is to share with you some things that we've learned about working with elementary school teachers, both just in general, and then as we've been trying to take first steps at helping elementary, both pre-service and in-service teachers working with the NGSS. There are a lot of really good opportunities and a lot of reasons why it makes so much sense to target elementary school teachers and early childhood teachers, for that matter, as well, around the NGSS. If you've spent any time at all with young children, you know that they have a very inherent curiosity about the natural world. And that natural curiosity that they bring when they enter kindergarten isn't always so evident by the time they leave elementary school and head into middle school. So there's a tremendous opportunity here to really help children foster that natural creativity about the world, and also particularly as it relates to underserved populations and underrepresented populations in the earth and space sciences. There really are two issues here when we think about working with elementary teachers. The first one is just the whole notion of working with elementary teachers in general in science professional development and some of the unique challenges that that brings. And then the second one is particular to the NGSS and implementation of the next generation science standards. As Susan mentioned, I'm currently at the University of North Florida. This is my fourth year here. Prior to that, I taught at a small liberal arts college in Pennsylvania, where in addition to teaching methods courses in science for pre-service elementary and early childhood majors, I also taught a content earth science course specifically for elementary school teachers with an associated lab. I do have experience myself as a classroom teacher in both elementary and middle schools. I've taught in both suburban and urban settings. And I've done professional development for in-service teachers in addition to my work with pre-service teachers. For the first year and a half I was here at the University of North Florida, I was called a professor in residence at a local urban elementary school where I worked primarily with the third through fifth grade teachers around science and in really helping children learn to engage in science and engineering practices. And I have also done some professional development for a school here in the area that is working to implement the NGSS.
Hi, everyone. This is Heather Pekovic, and I'm very happy to be here today. I'm currently at Western Michigan University, where I have a joint appointment between the Geosciences Department and the Mallinson Institute for Science Education. Oh, gosh, I've been here for about 12 years now, and my main teaching responsibility is an earth science content course for pre-service elementary teachers, and in Michigan, that is pre-kindergarten through 8th grade. I also do departmental advising for our secondary earth science and integrated science majors, and I teach a couple of content courses for those programs as well. For the past 5 years or so now, I've been involved with the MyTAP and the MyStar programs. These are two statewide professional development programs that are run by Jackie Huntoon out of Michigan Tech. And in particular, the MyStar program has focused on developing integrated science curricula for middle school grades. I did want to also mention, as part of my introduction, that Michigan is not an NGSS adopting state. A couple of months ago, we adopted our own set of K-12 standards, but when I read those, they are almost word for word identical to the NGSS. So even though we are not an adopting state, we have our standards were very, very closely modeled after the NGSS.
Yeah, that's a good point. I'm so glad you mentioned that, Heather. I should have said that in my introduction as well. Florida also has not currently adopted the NGSS. They did have a public comment period shortly after the NGSS came out, soliciting input from people as to whether or not Florida should adopt the NGSS. They, because of issues with adoption of Common Core, decided to delay decision on that process as to whether or not they would do that. Florida's history is to not really ever adopt anything wholesale. So even Common Core, they've made some changes and probably would make some adaptations to the NGSS as well. But nonetheless, in Florida, you're already seeing things coming from the state that are clearly being influenced by the NGSS. This whole notion of 3D learning is a new way of thinking for teachers, particularly for elementary teachers, whose own science learning very often focused exclusively on knowledge acquisition. Many of them describe not so fond memories of memorizing endless things in middle school and high school. And so for them, science is really just about knowledge acquisition. And that's a real change for them to think about the NGSS emphasis on not just what students will know in each grade level, but what they can do with that knowledge, and really hence creating the language of performance expectations and the importance of that. So there really are a couple of challenges here that relate to those three dimensions of the next generation science standards when it comes to working with elementary, in-service, and pre-service teachers. The first one is what we're terming the content challenge, and that is elementary and early childhood teachers' fragmented knowledge of core ideas in science, fragmented knowledge of those disciplinary core ideas, and real difficulty with cross-cutting concepts and seeing how ideas in one science domain would connect to others. The second area that's a challenge when working with elementary teachers is what we're terming the How Science Works challenge. Because elementary school teachers also have some misconceptions, frankly, about what it means to understand and do science, and what science and how science proceeds, which really relate to the science and engineering practices. And then something that's not so much related to the NGSS itself, but really is this issue of time. There's a lot of pressure right now across the country for teachers, particularly at the elementary school levels, to concentrate almost exclusively on English language arts and mathematics, which are the subjects that are tested yearly in grades 3 through 8. And the message that's being translated to a lot of elementary school teachers is that we'll do science after the test is finished, unless we happen to be in the grade level where science is being tested. And all of those really come together and make it hard for teachers to persevere when they go to professional development and leave all excited about how they're going to implement science in more authentic ways in their classrooms. Sometimes they then find it difficult to persevere.
Okay, well, I'm going to kick off talking about our content challenges. Within the DCIs, we found two big challenges to elementary teachers' proficiency with the content. First is science phobia, and the second is alternative suggestions. And so we're going to go over a little bit of detail about each of these and then provide some suggestions based on our own experiences and drawn from the literature for addressing these different kinds of challenges. So first, related to science phobia, it's important to keep in mind that elementary teachers are most often trained as generalists. So they have minimal science content preparation, not because they inherently like or dislike science, but because their programs of study have to include science and math and social studies and history and English and language arts and all of their education preparation classes as well. So the time allotted for science can be very, very minimal. Some teacher preparation programs have as few as 1 or 2 science content courses. I'm very fortunate to be in a university where our students have 5 science content courses, which is an awful lot. So because elementary teachers have often minimal science content preparation, they can experience a high level of math and science anxiety, and that in turn can lead to low confidence and low self-efficacy for teaching science. And a lot of the literature suggests that self-efficacy, or your belief in your own abilities to achieve something, can be a big motivator towards doing something, or a big distractor, and force people into avoiding doing something. In turn, what we often see is elementary teachers who tend to avoid teaching science in the classroom because maybe it makes them a little uncomfortable because they don't know that material quite as well as they think they should in order to teach it. So some suggestions oops, I lost my button here, excuse me, for addressing science phobia. And these are drawn mostly from my experiences, having worked with pre-service teachers over the years. We've found some small changes in our content classes and our methods classes for pre-service teachers, and this would probably work with in-service teacher professional development as well, can help address this dislike to even perhaps an outright fear of science. The first is the language that we use every day when we talk about what we do in class. And this idea comes from the arts, frankly. We stole this fair and square. In music class, when the children come in, the teacher says, all right, musicians, get your instruments, let's go play. In dance class, we say, okay, dancers, take it from the top, get on stage and go. So why aren't we using the language every day when we start our class? Okay, scientists, let's get up there and let's do science. This is a suggestion made by one of my graduate instructors, and just anecdotally this semester, she's seen a change in students' attitude and a change in how they think about themselves as actually practicing scientists from the moment that they step into class. So even a small tweak in how we talk to our pre-service and our in-service elementary teachers as them being scientists can have a big effect on their attitudes towards scientists. Something else that we like to emphasize is that it's okay not to know, because science is about not knowing and finding out. So we use a lot of inquiry activities, such as the one in the picture here, where they're using a fracking model. We start with questions, not with confirmation. We have students work into groups so that they have peer support, so that emphasizes the group work rather than anything competitive. Finally, we can connect science to relevant local issues. Most of our students are from the Great Lakes region, so we pick topics like lakeshore bluff erosion, or as you can see in the picture where the student is working with a model that reproduces fracking. So we talk about issues that they see in their daily lives, and helping our students connect those issues can make science a lot more relevant and a lot more interesting for them. The next thing we have to think about are alternate conceptions. And alternate conceptions are very deeply held incorrect to partly correct ideas about scientific phenomena. So they're not just that individuals are wrong and they can recognize that they're wrong. It's that these ideas are very deeply held and it can be hard to change them. And there's a lot of great examples of alternate conceptions in the literature. A lot of children and even adults think that, for example, that groundwater is hosted in giant underground lakes and rivers instead of in the pore spaces in between sediment grains. And there's some really good literature about alternate conceptions. But this can be a challenge to learning in my example here. So here you are in the classroom, and let's imagine I'm trying to teach a lesson about plate tectonics. Well, not only do my students come into, or my children in this case, come into the classroom with wildly varying ideas about what I mean by plate tectonics from their prior knowledge, but even after teaching, maybe some of them are able to incorporate the new conception into their mental frameworks, and maybe some of them are partially able to do this, and maybe some of them just kind of don't get there at all. So it can be a big challenge to determine what ideas your pre-service or your in-service teachers hold when they come to class or come to professional development, and whether you're actually changing these ideas with instruction. So some techniques or suggestions that Kim and I came up with. One is the importance of eliciting prior knowledge through probes. One thing we do in the class, which is featured in this picture here, is we start each classroom lesson with before you begin questions. So we have a series of questions that's just intended to draw out prior knowledge and draw out incorrect conceptions, alternate conceptions, about whatever topic we're going to talk about that day. I've also used some of Paige Keeley's formative assessment probes. There's a whole series of these uncovering student ideas in science books that I found to be helpful. And the new book on Earth environmental science probes just recently came out, and these are available through the NSTA, the National Science Teachers Association. Another technique that we use in class a lot is to phrase alternate conceptions as children's ideas. So the research literature shows pretty clearly that people hold the same alternate conceptions from their late childhood years all the way through their adult years. And so I know that if I, confront the alternate conceptions of my students by saying, oh, you're wrong, that's just going to make them very uncomfortable. But if we phrase that as, these are ideas that children have about this phenomena, this is what children think about plate tectonics, this is what children think about groundwater, or whatever our topic of the day is, I can sort of slyly address the misconceptions or alternate conceptions that my own students hold, but yet phrase it in a non-threatening way so that it's coming across as these are the ideas that you will probably encounter in the classroom with the children that you're going to teach. Finally, something else that we typically do, if we're going to recognize alternate conceptions, we're going to address them, we're going to explicitly talk about them in a class or in a workshop, I want to assess those. So on every content exam that we do in my class, we have our students actually identify alternate conceptions and distinguish those from true scientific statements, and then correct the alternate conceptions, and they get graded on that. So I do expect them to know and recognize alternate conceptions.
All right, so when helping students, then our pre-service teachers or thinking about in-service teachers, helping them with their own content knowledge, looking at their alternative conceptions, the other thing that comes into play with this content challenge is their ability to actually unpack the standards. We talk a lot in science ed and in methods courses about unpacking standards, figuring out what's actually in there. Unpacking the performance expectations in the NGSS is a bit more complicated process because they are more conceptually difficult than what many elementary teachers are used to. I've just put up an example here from the current Florida benchmarks for second grade dealing with earth materials, and then what really would be a comparable benchmark from the NGSS in the sense of dealing with the same things. If you look at the Florida benchmarks, they very much are focused on declarative knowledge and just that acquisition. Whereas when you look at the NGSS, there's a lot more depth to them. Elementary teachers sometimes find it challenging to unpack the kind of standards that you see on the left, and that will be even a greater issue with the NGSS and the ones on the right, because that greater depth also demands more connected knowledge. So any kind of professional development done with in-service teachers or in working with pre-service teachers around the NGSS, there really has to be some time spent on what actually is inside this benchmark. If you look even at, and this particular part, of course, is from the framework. It's from the NGSS, sorry. When you look at that, thinking about what do second graders and their teachers need to know to be able to meet that performance expectation. Well, a lot of the things that are in those more declarative kinds of benchmarks that you might find in other states, certainly things related to sediment size, composition of soil, things related to weathering, erosion, deposition, how sediment size, slope steepness affect the ability of water or wind to erode earth materials, even some things, rudimentary ideas about forces and the relationship between the size of the force and the change in motion. And so being very explicit in terms of helping elementary school teachers be able to figure out what is implied in these performance expectations and the kinds of knowledge that students will need to acquire to be able to meet these performance expectations is going to be important.
So the second of our challenges focuses on the science and engineering practices from the NGSS, and in particular we decided we would talk about how we can teach nature of science and then how we can integrate science with math and language arts in the elementary classroom. So nature of science, I'm assuming most folks know what this refers to, but the NGSS particularly uses the language of practices, and this refers to both children understanding how science works, how it's practiced by scientists, and then the ability of students to design and carry out scientific investigations. And the language on the slide there is from the NGSS themselves. So nature of science is very closely related to this, and I like how the NSTA portrays nature of science. It's closely related to the scientific practices, as exemplified by this position statement. We can think of nature of science as referring specifically to science as a way of knowing, and that it follows specific rules for what constitutes evidence, explanations, and the methods by which science works. So within the NGSS, if you look at Appendix H, and at first I did not know that the NGSS had appendices, but I recently discovered Appendix H. There's a whole section that addresses nature of science and provides this list of basic understandings. So this is from the NGSS. And in the narrative that goes along with the list, the document says that the first four of these, understanding that science involves a variety of methods, it's based on empirical evidence, knowledge is open to revision, and we use models, laws, mechanisms, and theories. Those are related directly to science and engineering practices. And then the latter four, science as a way of knowing, we assume order and consistency in the systems. It's a human endeavor, culturally based, and there are questions about the natural and material worlds. Those relate directly to the cross-cutting concepts. The other thing to know about this appendix to the NGSS is that it presents a matrix of nature of science performance expectations for the different grade bands. So they have performance expectations for K through 2, 3 through 5, for middle school, and then for high school. I just saw the comment, yes, I really like how much work they've put into supporting people with implementation. So from the literature, Kim and I talked about two suggestions for addressing nature of science within the NGSS. One is that the literature is pretty clear that an explicit and reflective approach is really important. If students are just doing science, they're doing their labs, they're doing their activities, they're collecting their data, but all they do is do it, and they don't stop and think about it, they tend not to gain any knowledge about how science is done. It's only when we stop and we ask students explicit questions that requires them to go back and think about what they've just done in their science activity that they develop a better understanding of what it means to do the science. So as an example, here are some in-service teachers that I worked with a couple years ago playing with their stream table. We often use physical models in a class. I'm sure, oh, thank you. Forgot to switch the slide. Thank you very much. I knew this was going to happen. I'm trying to do this on two screens at once. But so now that you can see the picture, the teachers are working with a stream table. So one of the things we do is when we work with a physical model, using models is a nature of science understanding. So we ask the students to explicitly consider how did we construct the model? What are the advantages and disadvantages of using this model? How is this model a good and not such a good representation of the real thing? How would other scientists use the model? So we make this reflecting a part of the work that the students are doing while they're doing it, and then a little bit after that as well. And yes, we also assess for this as well on exams. Another really good technique is to use history of science. So you can use case studies and historical examples to illustrate nature of science. This is particularly useful in illustrating the tentative nature of knowledge in science and to talk about how scientific knowledge can change with new evidence and new ideas coming to light. I have a colleague who teaches several of our biology content courses for pre-service elementary teachers. They use work from Kettlewell and the peppered moths. They use Mendel's work, and they've created a whole series of these historical case studies that guide students through how the science of biology has changed. And in addition to that, it teaches the content. So the content and the nature of science are closely embedded with one another.
I've also been watching the chat as Heather's been talking, which is a pretty cool device. I really like this. I wanted to just briefly comment on something there, which we should have probably mentioned earlier. In some of the work that I've done with in-service teachers, they do find reading the NGSS to be complicated and overwhelming because with the colors and with all the different information that's there. And so I've done some work with helping them read those. But one of the things that I have gotten in terms of feedback is that I've had some teachers say to me they don't see what they thought they were going to see in them. And one teacher said to me a few weeks ago, I'm really bothered about this NGSS. I don't know if I like them because I don't see the scientific method there. And so I think there really is going to be it really is going to be important to help teachers work through some of those kinds of issues and questions and things that they have. Many teachers come to me, pre-service elementary teachers come with a heavy reliance on believing that all science is done following the scientific method. At the beginning of the semester, they write a reflection about themselves as science learners and expectations for the course and all of that, and many of them talk about the scientific method. With them, I'm able to be very explicit and pretty direct about the fact that science proceeds by multiple methods and all those kinds of things. I've found it personally best to be, I don't know if I would say gentler or certainly more careful with in-service teachers because for them there is a sense of perhaps being embarrassed if they say something and feel like then in a group that they've been corrected, that sort of thing. So the being accurate is important, but strategies that were discussed earlier, like the formative assessment probes, are good. There are, for example, some formative assessment probes regarding scientific methods in Page's books, things about terminology. Theory, of course, is a big one. It comes up most commonly when talking about evolution, and pre-service teachers in particular will say, oh, well, that's just a theory, not really understanding how we use that term in science. So the difference between science definitions and the way we use words in common everyday language is important. Law is another one. Argument. Obviously, we're talking a lot in the NGSS about constructing arguments from evidence. For many elementary school teachers, the word argument has a negative connotation because it sounds like yelling and slamming doors and all those types of things. The other area to think about are terms that pre-service and in-service elementary teachers often overgeneralize, words like hypothesis, experiment, where every investigation is an experiment, and they think every investigation has both an independent and a dependent variable. So there are issues there that you always have to be aware of when doing work with them. Heather showed a really nice stream table. This is my elementary version of a stream table, and this really speaks to something that, let me see who it is, or Matthew typed in earlier on in the webinar, which is the whole issue of resources. One of the things that I emphasize a lot with my pre-service teachers is how you can do these things very affordably. So this particular stream table is a very elementary school stream table, done obviously with a cookie sheet that you can buy for $1 at the dollar store, or sometimes you can even get them less at Walmart, Target, someplace like that, and very simple kinds of materials, but still enables you to test some of those variables which are important for them to look at. The way, though, to really leverage vocabulary in a way that also helps deal with the time issue is to help elementary school teachers realize that there are terms that they're using in literacy and also in mathematics that, in fact, we use the same way in science. My pre-service elementary teachers are very surprised when we're talking about science and engineering practices, and we talk about how when we predict in science, we're really doing the same thing as when you predict in literacy when reading a story. And that's really important for them because as a group, they do like teaching literacy. Maybe people go into the profession because they're very interested in that. And so helping them see how things like prediction, like inference, like argument, analyze, the last two in particular, that are very much linked to mathematics and the kinds of things that you do, but also literacy as well. I thought about in preparing for this, as Heather and I were talking about this, we were thinking about some ways where there really is this kind of connection between these practices across disciplines. That if you look at the NGSS, Science and Engineering Practices, and then you look at the Common Core Standards for Mathematical Practices, or the English Language Arts Anchor Standards for College and Career Readiness, what you notice is that both the science and engineering practices and the standards for mathematical practice emphasize reasoning with models and also emphasize the importance of mathematical and computational thinking. When helping elementary school teachers really embrace the notion that they do, in fact, have time to teach science, helping them realize that they can meet standards in both mathematics and science at the same time is really important. All three of these areas really come together in when you think about making evidence-based arguments. That includes critiquing others' reasoning, both orally and in writing. It's a huge part of the English Language Arts Anchor Standards in the Common Core. It's also an important part of what students do in those standards for mathematical practices. And it's not a case where as people who engage in professional development, who are not professional educators per se, find themselves in colleges of arts and sciences or other places, that you have to suddenly know lots about these things. But it's just more, I think, really just kind of reminding teachers that, yeah, this is a part of that. And these things really work in both ways. When you think about reinforcing mathematics skills, again, it's a matter of reminding teachers that measuring does reinforce mathematics standards. A challenge that you may discover, if you haven't discovered already, is that measurement does become an issue with elementary school teachers' understanding of base 10 relationships, particularly if we talk about metric measurement. Sometimes pre-service elementary teachers aren't really sure how to read a meter stick. And then issues with fraction concepts as well. So it's something to be aware of when you have teachers who are measuring, just to be aware that those might be issues. Representing data obviously is important, and having teachers practice graphing data and determining which graph is appropriate for that type of data. Many elementary teachers' go-to graph is a bar graph, but they're not always sure why a bar graph is appropriate or what kind of data is appropriate for which type of graph. So helping teachers think through that for the particular area that you're working with is really important. One of the things that I like to do which really kind of focusing on this earth materials and systems from seventh grade that we've talked about earlier, is there's a great book that I use a lot with students. It's called Dirt, and talks about soil and has lots of interesting information about soil that I read to my pre-service teachers. There's a book that's very similar to it that's called Sand, both ones that I'd highly recommend to you. What I have students do in this whole section is we investigate the composition of soil and we observe soil samples. If we were to observe soil samples from my local area, if I went out and dug in my backyard, I'd get a shovel full of sand, and that would be about it. So typically what I do is I actually carry my gallon bags and my trowel with me when I travel around places and when I'm not flying, anyway, when I'm driving. And I've collected soil samples from different places, and I usually have pre-service teachers then observe soil samples from different places. And so I try to get those that might have different mixtures, of various components, sand, clay, and silt. And we also do the stream table that you saw, which actually there are directions for that in an article that was in Science and Children in NSTA's magazine for elementary teachers a few years ago. And we also investigate wind erosion using sometimes a straw or a small fan where children can do that. Elementary teachers really like actually engaging in the investigations as part of the professional development that they would be doing with their students, and then really, in many of the ways that Heather talked about earlier, really unpacking those and figuring out what they mean for them. The thing that really ties all this together, I would say, is this whole notion of perseverance. And that is, it's pretty typical for elementary school teachers to go to a professional development workshop and on whatever topic, and they get really jazzed about it. They're excited, all these things they want to do, but then on Monday they're back to the routine. Or sometimes what happens is they'll try something once or twice, and often the first time through it's a little bumpy. Because you still are coming up against their own self-efficacy and concerns they have about their knowledge and worries that a child might ask a question they don't know the answer to and all those kinds of things. So it's really important that we support elementary teachers in ways that will help them persevere when there's a lot of factors that conspire against them, many of which we've already discussed. One of the most important areas really is this need for sustained interaction. One-shot professional development rarely results in implementation. And the Laux-Horsley citation here suggests that typically teachers need somewhere in the neighborhood of about 50 hours of professional development to be able to really make something their own. Now, that's far more than what many districts allot for professional development or are willing to pay for. But it is important that if you have a good relationship with a local school district, that you really emphasize to them that there is really a need for this kind of sustained development. And there really is a need to help teachers be able to put it all together. And again, to be able to unpack those standards, to really figure out what they're saying, to be able to think about some of the alternative conceptions that children will bring to the table, to be able to think about their own knowledge, to be able to think how this particular area really connects to other areas via cross-cutting concepts, how these practices that students are engaging in are similar to practices in other disciplines are important. If, as a professional developer, you feel comfortable going into an elementary school teacher's classroom and co-teaching with them, it's really a good thing because it does establish credibility. Many times I've sat in professional development with elementary school teachers to hear them say afterwards, yeah, well, that sounds nice, but this person could never do this with my students. And so being able to establish credibility is important. quality resources are important, as has already been mentioned in the chat. There are a couple of social media sites that can be beneficial for teachers, particularly if you are in a situation where the school district is not willing to really fund a more sustained kind of involvement. One is called Edmodo, and it really it's a site for teachers to really connect with one another. Another one that some of you may be familiar with is Adapting Science for Kids. It's the ASK project, Teacher Helping Teachers, which has a lot of good science investigations, teacher developed, that are helpful. Directing teachers to those kinds of sites, particularly the ASK project, is important because for many elementary school teachers, their go-to site is Pinterest, which has not everything, not everything that's necessarily beneficial. And Science in Children, obviously, is a great source. If monies are available, then possibly a one-year subscription for teachers. Bill Robertson does a column every month called Science 101, which is focused on helping teachers develop their science content knowledge. That's really important, and they're nice. They're very well-written articles. In terms of issues also with resources, workshops that are make it, take it, where teachers leave with resources that they can use. These are really important and really do increase the likelihood that they will actually persevere. And all I think we'd end with really saying that from our experience, it's something that really is worth it, that the opportunities are there. I was just recently grading an assignment from a pre-service teacher who was in a kindergarten classroom and reflecting on the ability of these kindergarten students to engage in science and engineering practices, and how surprised this pre-service teacher was to see that kindergartners could do that. And this person said, even in kindergarten, students were showing the ability to make claims and have conversation based on the data they collected. It was fantastic. And that's what I think we want elementary school in-service and pre-service teachers to leave professional development with, because it's only going to benefit their students.
So thank you very much. Boy, that's a lot of food for thought, and I'm wondering what questions people have. If you have a question or something you'd like to have the speakers say more about, would you please type into the chat? Let's see. I'll need to come down and see that. You can see some people are typing.
Mm-hmm.
Well, people type their questions. Maybe you can comment on the idea that Joanne mentioned about the idea of having a visiting scientist in the room, similar to the co-teaching idea that you were talking about, having a visiting person in the room that takes the teacher and the students through material or activities. Is that helpful? What would you say about that?
I'll fill that one. I would absolutely agree with what you said, Susan, that the important thing always is that the teacher then is able to transition into doing that. That it's not viewed as, okay, they'll do it, I'll watch, I'll participate. But yeah, anything that builds capacity with teachers themselves is important.
Mhm.
Yeah, I would also say that I think it's really important that it's a two-way partnership between the scientist and the teacher. The teacher's going to know really, really well what their students can do and what they can understand. And I'll just throw in a little anecdote. One of the very first times I ever did any kind of outreach, I did a little presentation for kindergartners. And I had this beautiful poster that me and the other student, we were graduate students at the time, we put this beautiful poster together, and we show up in the kindergarten class, and I said, who can read this word and tell me what it is? And the little girl in the very first row raised her hand and said, we're only in kindergarten. We don't read yet. So there went my entire poster that we were attempting to get the students to look at. So as long as it's a two-way conversation with the teacher, I think it's a wonderful idea.
Gets back to know your audience. So Ed wonders, do you have a sense that some of what teachers know about instruction is working against their ability to implement NGSS? Maybe that's about the way that they've always taught before. What do people's prior ideas about instruction have to do with their ability to do this new kind of teaching?
Yes, I think that's how I would phrase it. It's about what they think they know about instruction, because you're right. I'm surprised still in 2016 that often with pre-service teachers, I'm still getting them to buy into the notion of authentic inquiry. We've been doing inquiry in science or teaching that we should be doing inquiry in science for a very long time right now at this point. And yet, because that hasn't been their experience, it is something that they have to buy into, to be sure.
Right, and then Ed follows up on that by suggesting, for example, the idea of, NGSS requires that we're looking at longer storylines as opposed to being wowed by every lesson and having shorter engagements.
Yeah, and that's a good point as well. And if I could kind of piggyback even then maybe with what Lindsay was asking, I don't know if this addresses her question, but really encouraging pre-service teachers to think more from a unit than a lesson perspective. Lessons over, a series of lessons, that becomes particularly important, and it really is required for the NGSS.
So is that what you would answer to Lindsay about the big tip? Start thinking longer term, more bundled storylines, longer cohesive sets of instruction?
I would. I don't know what Heather would add.
Yeah, I guess I haven't thought about this too much, but I do agree that NGSS requires a different kind of thinking, more long-term, and especially with the three-dimensionality of it, I think that's very hard to grasp at first. At least when NGSS first came out, I had the typical reaction of, oh, here we go, another round of standards. How can I tweak my class with small little changes to fit into this new model? And it wasn't until I started working with the MyStart program where we actually were unpacking the performance expectations. We were really spending a lot of time digging into the NGSS, but I came to realize how fundamentally different it was, and that it wasn't just perhaps little tweaks, but that it was rethinking the time commitment, the structure of activities, what we really mean to get people to the point where we can do this.
Well, and another thing to highlight is what you already mentioned, that in addition to the science learning, you're also getting at the numeracy and literacy things that are driving so much in elementary science. So you can do all of it as long as it's bundled and thoughtful, going from one unit to the next, from one lesson to the next. So another thing that I think is interesting here that Matthew brought up is that NGSS, one of its strengths is that students are revisiting concepts at a more sophisticated level from year to year. And so students may actually be asking questions in the elementary years that they don't yet know how to answer until later on. So is that a challenge? Is that going to be a challenge for elementary teachers, that not all the answers are in this lesson or this year? How would you speak to that recursive aspect of NGSS?
Do you want to take that one first, Heather?
Yeah, I think that could be a challenge, and I'm speaking more with my mom hat on right now rather than my pre-service teacher educator hat on, what I see my elementary school aged children, I have a second grader and a fourth grader right now, what I see them come home with is science is something that fits into neat little tidy boxes that they do a day here and a day there and a day here and a day there. And I think it is a huge challenge to weave that through longer time scales. And it will require a change of thinking and being okay with leaving things sort of open-ended and hanging, and then realizing that they'll come back to it at a later date.
Right.
Yeah.
And go on.
No, I was just going to say, and Matthew added something really important here, that that's part of this is really emphasizing to teachers that it's okay if they don't know the answers. That's why scientists do investigations, because we don't know the answers. That's the whole purpose. But that is unsettling to them at first, and it's particularly unsettling, I think, in science, but also in mathematics as well, in those two areas, because they're afraid that they do have this concept of a teacher as the person who knows all the answers.
I would agree. I even see that in pre-service teachers. But what's funny, anecdotally at least, I would say that I almost see that more strongly in my pre-service secondary teachers, that they, because they're meant to be content experts, they really feel like they have to know an answer. I was teaching my rocks and minerals class, which has a large population of pre-service teachers in it. And, when I would toss a rock out there and say, well, I don't know what the best answer is, they would look at me in shock, like, how can this not have an answer? So making everyone comfortable with, well, what I'm interested in isn't the answer, it's how you support your interpretation with evidence. Oh, okay. Then that seems to get over that hurdle of there not being a right answer, but that there's we don't use right answer in my class. We use what's the best answer and what's your evidence supporting that best answer. And by the time we've worked on that all semester long, then we can get used to the idea that there isn't a right answer.
That's interesting, and then a related question, thinking about parents' conceptions of science from Ed. Do you know anything about how parents view NGSS being used in classrooms, this new way of teaching?
I haven't had any conversations with parents. Again, because Florida's not adopted the NGSS, so the school that I'm working with is a private school, and I don't know. I don't have any experience with that either. Again, Michigan hasn't adopted, but again, with my parent hat on, we are a Common Core state, and so we regularly get, and the math in Common Core is very different, and I happen to really like it. I think my children have a much better grasp of mathematical reasoning than I ever had as a child. They can explain what fractions are and things like that. But we get regular communications from the principal of the school to the parents, explaining why you're doing math so differently nowadays.
Yeah, because everybody is used to what they think of as science teaching or math teaching. Not only teachers and parents, but also students who have done well in the existing paradigm. Change is uncomfortable for everybody. But I want to thank you for your presentation and for all of your thoughtful answers and thinking and strategies that you've shared with us, and just wonderful ideas, like even many of them really simple, such as "Okay, scientists." I mean, that's just profound, and I love that that some simple shifts can really change the tone of the classroom and how people are thinking about themselves as science teachers. Yeah. So we have 1 minute left, and with that, I want to let the people on the webinar know that not only do we have May 12th coming up, and we'll get that page open for registration pretty soon, but then we'll be taking a summer hiatus for a few months, and we'll be coming back in the fall We have a couple of things lined up already for the fall. One is about some best practices and some examples of how people are doing those first introductory workshops for teachers on how to approach NGSS. And another webinar is a tour from NSTA of what they have to support NGSS in Earth and Space Sciences. And also I want to throw out to the group that there are a lot of knowledgeable people who have been attending these webinars and have different things that they're working with. Kim and Heather very kindly came forward and suggested that this would be a great topic. So, if you have something NGSS related that you'd like to share, then please contact us. And I think you can find our information on. Let's see. Can you find our? Oh, there's our information. So you can contact us with ideas that you have, and on the evaluation. We are asking on this webinar, what else would you like to see? And we're also asking, where else do you get your NGSS information? Because that helps us know where we should reach out and maybe build partnerships. We'd like to do more and deeper programming as time goes on, so please tell us what you think would be helpful.
And that's the link, Susan, and that's the link that I just pasted into the chat box. So that's the evaluation. So people can do that. And I will be following up with an email to folks too.
Okay, great. So with that, I want to close out the webinar and thank everybody for spending some time with us. Please do, if you have colleagues that you think would be interested, please share with them the archive version. And with that, I want to thank our presenters again and wish everyone a great rest of your afternoon and evening.